Trees and forests are important features of most landscapes. They are usually visually dominant, are the foundations of many ecosystems, and can either fuel or hamper civilizations. The previous version of Mundus Vivus had forests. They were created during world generation and then remained static. Visually, they were represented by a single cloned model of a spruce, which was rather simple. There were no gameplay interactions, other than being destroyed when the user constructed the roads or buildings. The latest update has focused on making the forests more dynamic and to make them part of gameplay. To summarize, the forests can now grow and shrink over time. They are graphically more diverse, and certain user-constructed buildings can interact with them now. For example, lumber mills that harvest wood, or factories that produce pollution which decreases forest growth or even kills trees over time. How this has been done can be categorized into three parts. 1. Time-based dynamics. 2. Graphical representation. 3. Gameplay interactions. The landscape is made up of hexagons. Each hexagon has primary attributes like elevation, adjacency, and slope. They also have secondary attributes that are calculated based on the primary attributes. This includes land fertility, which at the moment determines the texture used for the map where there is no mountain or ocean. With this update, I've introduced a bunch of new secondary attributes that can dynamically change during the simulation, which was not the case for fertility. The fertility attribute was fixed. I refer to these new secondary attributes as fields. A field is basically just an array of decimal numbers. Here, visualized with a gray to red color map, gray being a value of 0 and red being a value of 1. The values are updated during runtime at certain intervals. My implementation uses burst compiled parallel jobs to efficiently update the fields during runtime. Burst compilation is a feature provided by Unity to compile C# code into highly performant native code. This can only be done under certain restrictions, like not using managed data types like classes or other modern C# features. One must instead write more pure, data-oriented code that uses simple arrays of primitive data types, which is something I like to do anyway. Combining this with multi-threading and ignoring a lot of Unity's default thread safety error handling means that I can perform a lot of calculations with barely noticeable performance costs. The forest density or biomass is represented as a field. The calculations performed for its dynamics are similar to those of logistic growth. The logistic function is typically used to model population dynamics in the field of ecology. It's based on the concepts of steady states and the carrier capacity. The carrier capacity being the state the system will naturally change towards over time if left undisturbed. In this equation, n is the population level, r is a growth rate factor, and k is the carrier capacity. I'm not using a pure logistic function, but rather a variation. Also, this is the time derivation and not the function itself. I removed the first population term, which is usually part of logistic growth. This gives similar but slightly different dynamics. The property of the carrier capacity still exists, but the fixed point at 0 is removed. This is by design. The pure logistic function has two fixed points, an unstable fixed point at 0 and a stable one at the carrier capacity. If the system is at either of these states, it will not change anymore. It's static. I think the fixed point at 0 is annoying, hence why I have changed the function to remove it. Without the 0 fixed point, the system is more stable and will not get stuck, which I would otherwise need to solve with some ugly workaround. Looking at studies of forest biomass over time, I think this adjusted function is still decently valid. In my simulation, the carry capacity is determined by the slope of the landscape and some initial Perler noise. It's also determined by pollution levels, which I will talk about later. The idea of just using slopes and Perler noise is not very advanced, but this can be improved upon later, taking into account moisture, sediment types, and pH levels, things that are typically important for tree growth. Trees used to be visualized with just one kind of model, the model of a simple spruce tree. I've tried making some additional low-poly models in Blender. I made a birch, a pine, and a kind of oak tree. It's pretty cool how a very simple mesh with some decent textures can look okay at a distance. In this kind of simulation, the trees don't need to be perfect when viewed up close because you're typically very zoomed out. The scale or size of the trees is determined by each hexagon's forest capacity value. Cells with high carry capacity will have bigger models. The density or number of models per hexagon is determined by the current value of the forest field. A hexagon can have a maximum of 1, 3, or 7 trees on it, specified by a setting I haven't yet exposed in the GUI, but will add at a later time. The build that's available on the itch.io page is limited to 3 trees per hexagon. From a more technical perspective, these trees are drawn using GPU instancing. For normal draw calls, the CPU needs to send a mesh, a material, and a transform for each object being drawn to the GPU each frame. At least that's how I understand it for 3D objects. This is, for example, how the landscape and the buildings are being drawn at the moment. I am using Unity and have been lazy in using their game object system, which is used by the landscape and buildings at the moment. But Unity provides a low-level API interface for doing all your draw calls there if you wanted. Theoretically, you could have a scene with only one single game object, all your draw calls being handled manually by you in the code, which is maybe a direction I will take going forward anyway, because of how I like to structure things. Anyway, this works decently when you're drawing a small number of objects, but will not scale well for an enormous amount of objects, which is the case for the trees. With enormous, we are talking tens of thousands, and I want to get up to 100,000. At the moment I can't, but that is one of my aims. GPU instancing is a feature that can be used when drawing a large number of identical objects. Identical meaning that they all share the same mesh and material, but have different transforms. With this methodology, the mesh and material, which can be very big objects, are only sent once to the GPU each frame, and instead an array of transforms are sent for each object. Transforms are just matrix 4s, which are very cheap compared to meshes or materials. The shader on the GPU side will then perform the instantiation or cloning. This is the technique I use for drawing all my trees, and it works pretty well. The Unity API provides pretty undocumented, but still very functional ways of invoking this in your main loop at runtime. Currently I can have around 50,000 trees and still maintain around 60 FPS, but 50,000 trees is stretching it. For a hardware comparison, I'm using a RTX 3070 for a laptop. There are further improvements I could look into to make the tree graphics even cheaper and faster. I, for example, am not doing any frustum culling or lodding. Frustum culling is the technique of only rendering objects that are actually visible to the camera. At the moment, I'm rendering all the trees on the entire landscape, even though the camera might be zoomed in on only a small part. I've not yet looked into this, but I believe it would be a huge performance boost, at least when being zoomed in. For viewing the world zoomed out at max, I think LOD levels would be something to look into. Now, let's talk gameplay. The user can now construct buildings that interact with fields. For example, the forest field. Here, a simple lumber mill style building will cut down trees in an area to produce some resource. This might seem simple, but it opens up for more complex building designs in the future. The possibly more interesting addition is the addition of pollution. Certain buildings will generate pollution as they operate. Pollution is represented by two dynamic fields. Air pollution is what is generated by buildings. It will disperse based on a simple wind pattern system. Air pollution will gradually get absorbed into the ground. Both the air and ground pollution will diffuse and decay over time. The carry capacity of the forest will decrease based on pollution. As the forest biomass decreases as a result of pollution, some of the visual tree models will change to dead versions. This provides visual feedback for when the player is negatively affecting the world, but I also think it looks pretty nice. This web of interactions introduces more strategic decisions for the player. For example, you need to be careful where heavy industries are constructed, or there will be no forests left to harvest. This interaction web is still pretty basic. It would, for example, be interesting to make forests and unpolluted wilderness something that is worth preserving. Some global level of ecosystem health could be measured to use as a scoring metric, rewarding the player for keeping their economy in check within certain bounds. One could also imagine entire scenarios based around polluted worlds, where it is the goal of the player to purify the world and to reintroduce wildlife, where the map will start completely barren and gradually get greener and more full of life as the player progresses. Another thing that could be explored with these dynamic fields are yearly seasonal variations. For example, by varying temperature and rain patterns over the year, one could model a winter-summer cycle. Visually, this could look pretty cool. Similar to how the tree models can change to a dead version from pollution, there could be autumn and winter or even spring versions of the trees, all looking slightly different, with orange, yellow leaves in the autumn, no leaves at all during the winter, and maybe young, bright green shoots and flowers during spring. I'm not so interested in combat in games. I think creation is more interesting than destruction. But I think these pollution systems or harsh winters could serve as challengers in their own rights, introducing hard and challenging gameplay without needing to introduce combat. So with these changes, the world has become more alive with dynamic forests. There are more interactions between the user's economy and the world. There also exists a good framework for implementing more dynamic fields in the future. So, what have I got planned next? This update has mostly focused on world simulation, and I now want to get back to more gameplay features. I've recently gotten some great feedback from users on my Discord server. Areas of improvement has been pointed out, which I plan to work on during the upcoming weeks. Apart from that, the GUI for constructed buildings is also something I want to improve. It's very crude and has barely changed since I implemented it half a year ago. There are some building data that isn't even visualized. Crucial data should not be hidden. I also want to make more features for getting an overview over all constructed buildings. For example, to be able to search for buildings that are not operating at 100% efficiency, so you can easily see where there are bottlenecks or other inefficiencies in your network. But apart from improvements of existing systems, I want to make new features as well. The two big things I want to do next is to add support for upgradable buildings and to add support for multi-tile buildings. Adding upgradable buildings would enable the user to further improve their economy without just constructing more basic buildings. It would also make the research system more vital and important. What I mean with a multi-tile building is a building that can occupy more than one hexagon. Currently, there is a limit of one building per hexagon, but you could imagine that the big factory would occupy more hexagons. For example, a triangle of 3 hexagons. And a huge monument could occupy a greater hexagon, i.e., a hexagon shaped out of 7 normal hexagons. My roadmap is not 100% set in stone, so if you have any suggestions for improvements, possible features, or just feedback in general, feel free to comment on this video or start a conversation on the Discord channel. The latest build is available for free on a new itch.io page I set up for this project. It's titled Mundus Vivus, being Latin for Living World, a title that I think represents what I want to capture with this project very well. I love simulations, and I hope you do too. Thanks for watching.